You can wait for 5 minutes, or we'll start from 6:05 and see if someone will join, and then we can start. You can skip the video to 6:05 directly, and we'll start solving the questions on BJT and MOSFET. Okay, let's start the session. Questions are again on BJT, and we will do a little bit of analysis on how to find input resistance, output resistance, and so some small thing analysis. Okay, so the first question is for the circuit shown in figure 4.1, consider the values of the different elements and the parameters in the common. Okay, so this is my emitter, base collector. What is given is RB is 470 kilo, RC is 2 kilo, beta is 80.
Sir, your voice is too low, sir. I can't hear you.
Uh, it should be clearly audible, I guess. Can you check your speaker?
What, sir?
Can you check your speaker? Go to your mic setting and see if you have properly set the
Okay, sir. It's
headphones.
okay. It's okay now.
It's audible now?
Yes, sir.
Okay. So the beta is 80. VBE on, when the device is on, then VBE potential drop across base and emitter is, sorry, I should write VEB on. VEB on is 0.6 volt. VEC sat, that means when the device is in saturation, the voltage VEC across emitter and collector is zero point 0.2 volt. Thermal equivalent voltage, if needed, let me just write millivolt. And early voltage, which is due to channeling, so not channeling formation, that is in MOSFET. So VE is 120 volt. That means the value when the transfer current is zero, when you draw the tangent from the saturation curve. So, okay, so the question is for the circuit shown in this figure, find the magnitude of small signal voltage gain. What is small signal voltage gain? That is V output by V input, but this should be small signal. So that is AC. Okay, assume the signal coupling capacitors are shorted while doing the small signal analysis. That means the C1 and C2 are shorted for this analysis. Okay, so I need to find this. Okay, let me just draw equivalent circuit, which will make it easier to understand how to get the answers. Let me just first short the capacitor. We short the voltage DC sources. This will be my small signal circuit, and its equivalent circuit will be like this. Right? I ignored R pi for now. So you know R naught, right? R naught is, do you remember the formula? Type in the chat box if you remember the formula for the R naught. VA is given, that is equivalent to 120 volt. Okay, so if you write KCL at this node, you can see V naught, V output by R naught plus V output by RC plus GMVS is equivalent to 0, right? And R naught and RC are in parallel. I can write V output 1 by R naught plus 1 by RC is equivalent to minus GMVS. This means V output by Vs is equivalent to Gm times RC parallel R naught. So this is my voltage gain. Now I need to know what is R naught and what is Gm. Right? So Gm from formula we know it's equivalent to IC by Vt. So remember these formulas. Or IC, we know IC is beta times IB. Okay. Now what is the unknown here? IB, right? So I need to find IB. Let's go back to the circuit. IB is this potential by RB. That is my IB because the current will flow here in this direction, DC current, right? This is my emitter current, this is base current here, and this is my collector current. This is how my IB will flow. That means it will be VB by RB. So my IB, VB, can I write VB as VE minus VEB by RB? Can I write it? Yes, right? Because VEB is VE minus VB and VE will cancel. It will again give me VB by RB. So now I know VE. VE is the applied DC voltage. This is VE, 10 volt minus VEB. VEB is given here, 0.6 volt, and RB is also given for 70 kilowatt. If we calculate this, it comes out to be 20 microamperes. Now IC will be beta times 20 microamperes, and beta is 80, right? Yes, 80. So this is 80 multiplied by 20 microamperes, comes out to be 1.6 milliampere. So this is my current. So this is important for further questions as well. So now GM will be 1.6 milli by VT is 26 milli. Milli and milli will cancel. This will be 1.6 by 26. Let's just keep it as it is. Okay, now my voltage gain. Again, we need to find R naught. R naught, as I said, this is equivalent to VA by IC. So this is the formula for R naught. Now we know IC, we know VA, that is given. How much? 120. And IC is 1.6 milli. And my R naught is, which is calculated again, 120 divided by 1.6, that is 75 kilo. This is my R naught. So my voltage gain will be V output by Vs is equivalent to Gm Rc R naught divided by Rc plus R naught. So that means my voltage gain will be Gm is 1.6 by 26 into Rc. Rc is 2 kilo ohm multiplied by 75 kilo ohm divided by 2 kilo ohm plus 75 kilo ohm, right? This 1k will cancel. So if I calculate it, multiply by 2, multiply by 75, this is 40 divided by 26 divided by 77, multiply by. This comes out to be 119.88, so I can write it as 120. So this is my voltage gain. Okay, voltage gain is, what is the unit of voltage gain? Just type in the chat box if you know. But we need to find the gain in dB. Okay, we need to find the gain in dB scale. Okay, so we have two formulas. One, if we have voltage, so in dB, if I need to convert in dB, I should write 20 log of AB, and if you have powers in dB, I should write 10 log of. Okay, let's say AB is the power, right? So now we calculated the voltage gain. So voltage gain in dB will be 20 log of 120. So that is log of, okay, Lg. Just be careful when you use calculator. There will be two. One is Ln and another is Lg. Just check uh, which log you have to use, natural logarithm or the other one to the base 10, and one is another is to the base e. So here we use to the base 10. So be careful. If you want to check in the calculator which one is what, you just do log of 1. If it comes out to be 1, that is log to the base 10. Okay, so this will be your check. So comes out to be 41.58 dB. So this is our gain. Okay, so if you have questions like this, I hope you can solve these now. So next, we have to use the same circuit, okay, and solve the other questions. Find the small signal input resistance and output resistance for the circuit shown in figure 4.1. Let me first try to copy this circuit. One second. Okay, anyway, I'll just Draw this in. What we need to do is we need to find input resistance and output resistance. So in the previous session, I showed a method to do so. That is to add a test source and find the current flowing and do the KVL or KCL. You will be able to find the resistance in the circuit. So here we need to find the input resistance first. Let's say that. So let me just draw the equivalent circuit. Just let me know. And know that this is small signal input resistance, so we will short the capacitors. This will be my RB. Let's draw first the equivalent circuit. Let's call this voltage as V in. Okay, this is my VR. So if I need to find the input resistance, what I will do is I will attach a source Vx such that current Ix is flowing. That means V in is at potential Vx, right? So now the Ix is flowing through RB and R pi, right? So if we assume R pi is very large, like we ignored in the previous question, what we can do is the current Ix will flow through IB. So Vx will be Ix times RB. So that means Vx by Ix, that is my R input, will be equivalent to RB. This is without R pi. Similarly, if you now, I know that when you apply the signal at input, you need to ground the output. Okay, so this needs to be done. Okay, now I need to find the output resistance. So what I will do is I will attach Vx, Ix here. Input will be grounded. When input will be grounded, that means V in is 0. That means no current flows in this branch. All Ix will flow through RC. Right? So my Vx will be equivalent to Ix times RC. That means Vx by Ix will be R out, will be equivalent to RC. So this is without R pi. In any case, it will be again equivalent to RC. Okay. Now let just give you an work to do by yourself. Yes, if you want to ask anything, please. Now find the input resistance. Including R pi. I hope you can do that. If you are not able to do that, please let me know in the next week. Okay, so this should be easy. You will know to. So if you want to, if you raise, someone raise the hand, right? So if you want to ask anything, you can just type in the chat box or unmute yourself and ask the question. Okay, so this should be easy, right? So you just need to add the input source and include R pi in your calculations and then find the answer. Just Vx by Rx. You need to find Vx by Rx. Okay. What next? Find the value of signal coupling capacitor C1 such that the lower cutoff frequency of the amplifier is 200 radian per second. Okay, we need to find omega. Always remember that there are cutoff frequencies, lower cutoff. We will, I guess, in the next session or next after next, we will study these, or you will have the lectures on the cutoff frequencies, and you will get to know that for the lower cutoff frequencies, your input circuit is responsible. Here also, the signal coupling capacitor C1 is at input. So we need to find the lower cutoff frequencies of the amplifier. Okay. So if I draw the circuit, I hope you will be able to understand now how to draw the circuit. This is RB, R5. In the previous part, I also ignored R0. You can include the R0, then total output resistance will be RC parallel R0. It should be simple now. Just add the test source, check the current, and then do the test source by test current. You will get the resistances. Okay. Use this equivalent circuit to find the input resistance and the output resistance. I hope you will be able to do that. Now we need to find lower cutoff frequency. Okay. So this is my Vs here. This is V in here. Let's find V in. V in will be R pi parallel RB divided by R pi parallel RB plus XC1, right? This is simple voltage divider. We have C1 and then we have R pi parallel RB. Okay. If you don't understand some things, you can clearly stop me. Okay. So this will give me V in. Now, if I do a nodal analysis here, I can find V out by RC parallel R0 plus Gm V in is equivalent to 0. So this means V output by V input is equivalent to minus Gm RC parallel R0. Right? And in terms of Vs, I can write V output by Vs. If I take magnitude, will be equivalent to Gm RC parallel R0 multiplied by RB parallel R pi. Why I'm writing this? Because I have changed V in terms of Vs, right? So this was our formula. Why I'm writing square root? If z is a plus iota b, then magnitude of z will be square root of a square plus b square, right? So that's what I have done here. V in is r pi parallel rb divided by r pi parallel rb plus xc1. Xc1, what is xc1? This is 1 by j omega c1. All right. So that's what is written here. So now if I do some calculations, so if I just don't take the magnitude, just directly write it as this, and then the GM 1 by j omega c1. So we can now write the pole. Pole will be at 1 by omega c1 equivalent to rb parallel r5. So it's like this. If you have a transfer function, let's say this is s1 minus z1 divided by s1 minus p1. In the denominator, for s equal to p1 is the pole, and you may have studied this in your control systems, right? And s is equal to z1 is 0. 0 is when your transfer function goes to 0, and pole is when your transfer function goes to 0. So here, that condition is when 1 by omega c1 is rb parallel r pi. Alright, so omega, which we have to find, that is lower cutoff frequency, will be then 1 by rb parallel r pi multiplied by c1. So this will be my lower cutoff frequency. Okay, r pi calculated in previous section, and rb you know, and c1 is given. I guess we have to find others. Okay, we need to find c1, and omega is given. So I did the opposite. So we need to find c1. This will be omega times rb parallel r pi. Just find this, right? This is now easy. Okay, next question. Find the maximum output signal swing without significant distortion for the sinusoidal input of the circuit, as shown in figure 4. This figure is saying what the question is saying, that if I have input signal like this, my output signal, which will obviously be amplified in common emitter mode, should not be distorted. That means it should be sinusoidal as well. Okay, so this is input sinusoidal, it should be sinusoidal at the output as well. So this is what the question is saying. So we have transistor. Let's see this one. This is our V out. So this is our figure 4.1. You can put figure 4.1. This is, and it is given that V sat is VEC sat is 0.2 volt. So what this condition will give us, it will give us a condition on V out, maximum condition on V out, such that the device remains in the saturation. Okay. So whenever you design an amplifier, you keep the device in saturation, and in this way, if I just calculate this by using the KVL, I will get a maximum condition from this to this for the V out. So that is 10 minus 0.2 volt minus V out is equivalent to 0. Okay. So now I need to find the quiescent condition. Okay. What is quiescent condition? Q point. Swing is for AC analysis, and at the bottom of it, we will have some DC voltage and the current. So these are called quiescent points. like ICQ, IEQ, VCQ. These are crucial conditions. Let's find out. In the previous questions, we know IC is 1.6 milli, so VC will be IC times RC. This is RC, and VC will be 1.6 milli. RC is 2 kilo ohm, so my DC will be 3.2 volt. So we have DC is 3.2 volt, so this will be minus 3.2 volt. It comes out to be this is 3.4, 10 minus 3.4 is 6.6. So maximum AC signal on top of 3.2 volt, it can go to 6.6. So if I just plot this is my condition of 3.2 volt. Because only when V out goes to 6.6 volt, then the device turns off. And at a lower limit, there is the lower limit, it can go to 0. Right? Because if it goes to 0, my device will always be in saturation. Okay? So we have a swing of 3.2 possible at the bottom and a swing of 6.6 at the top. So always there would be a signal swing with the minimum distortion. We need a minimum distortion, so it should be the lowest case, that is 3.2. So we will have an output swing of total peak to peak to multiply with 3.2 volt, that is 6.4 volt peak to peak. So this is the maximum output swing possible without any distortion. Next is same question on same type. Find the maximum input signal swing for the circuit. Select the closest. Now we need to find the input swing. Easy, right? We know V output is gain times V input. So swing will be also proportional to gain. So my V input will be V output swing by gain. So this is swing here. The output swing we calculated in the previous question is 6.4 peak to peak divided by gain. Gain will be your GM times output resistance. The output resistance is RC. Let's take only RC. Ignore R naught. So this will be 6.4. GM is we calculated in the question, right? GM was GM is 1.6 by 26. And the RC is okay. So what is the total value? 6.4 multiplied by 26 divided by 1.6. Oh, sorry. 0.04 divided by 2. So the input swing will be 52 millivolts peak to peak. So this is the voltage swing at the input, and it will give you the voltage swing of 6.4 volt peak to peak at output. Pretty huge, right? Because of the high gain. Okay. Now the next question is on MOSFET. So, sorry, this again is on BJT. We surely have good questions on the MOSFET. For the circuit shown in figure 4.2, we have R1 given, that is this resistance. These are called biasing resistances. R2 given, RC and RE for collector and emitter resistances. VCC is the DC applied voltage of 12 volts. VEB on. So this is emitter, this is base, this is collector. So this voltage is given as zero point 0.7 volt. VEC sat is 2 volt, zero point 0.2 volt. So this is zero point 0.2 saturation. Okay. Beta is 100. Okay. Beta is 177. The voltage is very high. We also assume base loading of plus. Okay. Find the DC voltage between emitter and collector terminals. First, we need to find the DC voltage. Okay. That is VEC. We need to find this. Alright. Okay. For VE, can I write it as VE plus VEB? Right? I can write it because VEB is VE minus VB. This is VB here. That means VB plus VEB will be VB plus VE minus VB. So this and this we can see. I'm left with VE. So this is equivalent. Now what is VB here? VB is this voltage. Simple voltage divider. VB will be R2 divided by R1 plus R2 multiplied by VCC, which is 12 volt. Let me for now write it as VCC plus VEB. VEB is given 0.7. So this will be R2. R2 is 80 kilo ohm divided by R1, that is 40 kilo ohm, plus R2, that is 80 kilo ohm, multiplied by 12 plus 0.7. So this is 80 plus 40, 120. 80 by 120. So this will be VE will be 80K by 120K multiply 12, 12, 10. So this is 8.7 volt. Hope this is clear. Now I can write the value of IE. Look here, these are two terminals. I now know VE and I know VCC. What is the current flowing through RE? This is VCC. This is VE. Current flowing through RE will be VCC minus VE by RE. Right? VCC is 12. This is 8.7. Whereby RE is 3.3 kilo ohm. Alright, so this is 3.3 by 3.3 milli. So this is IE is equivalent to 1 million. Good. So now next, what is IE? IE is IC plus IB. This is a very basic formula for BJTs. Or I can write IB as IC by beta. This is also clear. So that means 1 plus 1 by beta, or IC is equal to beta plus 1 by beta. So now beta is 100 for this transistor. So IE will be IC times 101 by 100. So now to calculate IC, it will be equivalent to 100 divided by 101 multiplied by IE. That is 1 milliampere. Let me write here 1 milliampere directly now. Hmm. So this comes out to be, let's just keep it here and use directly the next step. So tell me now what is VC here. VC is this voltage. This will be directly IC times RC. So this will be 101 multiplied by 1 milli multiplied by RC. RC is 3.3 kilo. This we can see 100 divided by 101 multiplied by 3.3. So VC is 3.267 volt. Okay. So now what is VEC, which we had to calculate? VE minus VC, and VE is 8.7 and VC is 3.26. 8.7. This is equivalent to 5.4346 volt. So this is how you can calculate the DC points. Okay. Now the question says, one second. If you have any questions, you can ask, or if you didn't understand some things, you can ask that as well. Okay, what is the question saying here? If beta of transistor is changing to 300, then what is the DC voltage across the emitter and the collector terminals? Okay, so beta is now 300. What is the relationship between IC and IE? We know IC is alpha times IE, and I alpha is beta divided beta plus 1. So my IC will be equivalent to 300 divided by 301 times IE. My IE is 1 milliampere. So my VC will be SCRC, and my VC will be 300 divided by 301 multiplied by RC is again 1 milli. RC is again 3.3K. So this comes out to be 2W0 divided by 301 multiplied by 3.3. So this comes out to be 3.58. And now if I subtract it by, this comes out to be VEC, that is VE minus VC. This comes out to be 5.12 volt. This is again the same question as previous one. You can use the concepts which we used and solve the question. Okay, so now this is a good question. This will return the same things. Find the ratio of small signal voltage gains of the amplifier with and without bypass capacitor CE. So we have a capacitor which is called as the bypass capacitor CE for the circuit shown in figure 4.2. So this is my circuit. Let me just redraw it here. CE is the bypass capacitor. Okay, so we need to find the ratio of the small signal voltage gains. Let's say first one with bypass capacitor. With bypass capacitor, that means RE will be shorted, right? One second, we add CP to switch. Okay, this is my VCC. Okay, so this is CP. This is CP. So with bypass capacitor, CRE will be shorted. Let me just draw the equivalent circuit. So this will be, let's say, VS, this will be R1 parallel R2. You should know how to draw the equivalent circuit, then only you will be able to solve these questions easily. One second. Okay, C2 is not a cross. So this should not be like this capacitor shouldn't be here like this. Anyway, let's use this. So my V out will be, let me just directly write GMRC VS. So my gain, that is V output by VS, will be GMRC. So this is without the bypass capacitor, sorry, with bypass capacitor CE. So what does CE do? If I have CE here, it shorts the RE, okay, and this is directly grounded. Now, what if I have the bypass? I do not have the bypass capacitor. So without bypass capacitor, drawing the equivalent circuit. Now we have here RE as well. Okay, and here I should not write it as VS. This is B, this is E. So this should be here as VB. Now let's say at this node, what is VE by RE will be equivalent to incoming currents. This is a living current. It will be equivalent to incoming current, which will be VBE by R pi plus GN VBE, right? I need to find VE in terms of VS. So my VE by RE will be equivalent to R pi is, okay, sorry, GM is IC by VT. This is again VBE by R pi plus IC by VT minus VBE. Just simplifying it further, VE by RE is equivalent to IC by VT, let's say VE minus IC by VT, VE, okay, plus VB by R pi minus VE by R pi. Just transfer the terms on right hand side and left hand side, you will get VE as 1 by RE plus 1 by R pi plus IC by VT is equivalent to, now what is VB? VB here is VS. So VB is VS. So I can write VE as IC by VT plus 1 by R pi divided by 1 by RE plus IC by VT plus 1 by R pi whole multiplied by Vx. This is my Ve. Now VEB is 4.7 volt. This is given. And I can write from the voltage divider VB as, you see from the figure, VB is this is V, so this will be VB. VB will be R2 by R1 plus R2 times VCC, right? That is, we have calculated it. It comes out to be 8.7 volt. Sorry, not 8.7 volt. That was VEC. This time out to be 8 volt. And if it comes out to be 8 volts, then VE is VB plus VEB, which is 8.7 volt, because VEB is zero point 0.7. And again, IE from the previous calculations, we can write here as well, 12 minus 8.7 by RE comes out to be 8.3 by okay. Okay, now you have VE, right? You have VE now. We will not do the calculations for now. You have VE. Now, what next? To find the gain. Just look at the circuit here. If you do a nodal analysis here, it comes out to be V output by RC plus GM VBE is equivalent to 0. So, my V output will be minus GMRC VBE. Okay, now you need to find VBE. Can you find VBE now? You have VE in terms of VS, gain is GMRC and VBE, and VBE is VB minus VE, and VB is VS, and VE is IC by VT plus 1 by R pi divided by 1 by RE plus IC by VT plus 1 by R pi times VS. So VBE will be 1 by RE plus IC by VT plus 1 by R pi minus IC by VT plus 1 by R pi 2 divided by 1 by RE plus IC by VT plus 1 by R pi times Vs. This and this will cancel. This is here. This and this will cancel. So my VBE will be equivalent to this Vs divided by 1 plus ICRE by VT plus RE by R pi. So this will be my VBE. Now you have to substitute this here. You will find the gain. I hope you will be able to do the calculations. Now next is finding the input resistance. You know the method, right? You know the method how to find the resistances by assuming the bypass capacitor is not present. Now this is important here. Bypass capacitor is not present. So let me just redraw the equivalent circuit. If bypass capacitor is not present, that means there is a resistor Re. Okay, so we need to find input resistance. This is R1 parallel R2. Just get the habit of drawing the equivalent circuit. So you will be able to solve the questions easily. So what if I do, I add a test source here, and when I find the input resistance here, then I do the parallel combination of that resistance. Let's say I get a resistance R dash. So my total input resistance will be R dash parallel to R1 parallel R2. So it will make the calculation easier. So let's say the Ix current flows through R pi, and this Ix will have some contribution to Re as well, right? Otherwise it was pushed down. Now let's do the KCL here at this node. Okay, what is the current flowing through Re? That is IE, which is IC plus IB, or beta plus 1 IB. So if I write a KVL from this node to this node, so this is at a potential of Vx. So Vx will be Ix R pi. And remember that here the base current is Ix, so I need to write here Ix as well. Ix IB is equivalent to Ix. So this is beta plus 1 Ix. So the Vx is Ix times R pi plus beta plus 1. Sorry, there is some difference. Here this should be Re, this is a potential drop. Beta plus 1 Re. So this is my Vx by Ix. This will be my input resistance, which comes out to be R pi plus beta plus 1 Re. Now, so what is, sorry, this is R dash, not, this is my R dash. And what will be the total input resistance? R dash parallel to R1 parallel to R2. Right? This is how you can find. Yeah. Okay, you just use the values from the previous questions, find R prime and get the answer. This should be not easy. So this shows the question. This question shows that you need to do the KCLs, KVLs, and just how I use the test source. I can use the test source here as well directly. Then it will have two components, so it gets a little bit difficult. So this one is the easiest approach because you know R1 parallel R2, and it will be parallel to your pole resistance. So the equivalently, this is like this. So what we did was we found out this resistance, and then this resistance is in parallel to R1 parallel R. Okay, should we continue this part or do the others in the next sections? We have, okay, let's just I'll directly give you some overview of the questions because you may have assignments which may have some same questions as well, some related to questions. Let me just give you a brief idea of these questions. So we need to find a small signal voltage gain, P out for V input. Assume the capacitors are shorted. You know, when the capacitors are shorted at the end, it becomes easy, right? C1 is shorted, so the gain will be GMRD, and you need to find GM and other things are given to you. Okay, so this is what we will do in this question. Again, you have to find the input resistance. Just directly tell me what will be the input resistance. If you have the circuit, input resistance will be R1 parallel R2. But you don't need to say directly. Draw an equivalent circuit, use the test source, and find the answer. Okay. Next question is find. Okay, sure. Okay, let me just draw the equivalent circuit. Small signal. C1 is shorted, and this VDD will go to ground. So this will be R1 parallel R2. This will be your VG, and this is source. So nothing is connected to source. It will directly connect to ground. This will be your GMVGS, and this will be your RD. And this will be your PR. This will be your equivalent circuit. Now from KCL, you can directly see V out will be minus GMRD times VGS. Okay. Now input resistance will be this resistance. Next is output resistance. Output resistance will be this resistance. And remember that when you attach a test source here, you need to short the input sources. So when I attach to find the output resistance, you need to short every other signal. So if I attach Vx at output, my Vin will go 0. That means Vg will be 0. That means GMVGS will be equal to 0. My output resistance will be simply RD because only this is the path where the current will flow. So my Vx will be Ix and RD. Vx by Ix will be RD. So your output resistance will be RD. But you need to draw the circuit, find the answers yourself as well. So this is the step. And at last you have to find the value of signal coupling capacitor C1 such that the lower same as what we did in the BJT part. Use the circuit, the small signal circuit I drew earlier, and do the same analysis I did for BJT and find the answer for C1. I hope you can do that, right? If you're not able to do that, we can repeat it in the next session. Okay, when is the next session? One second. Okay. Okay, so I don't think uh, I can present the next session because I have some personal function to attend. So we will meet on 30th. We will have two sessions on 30th. If you have doubts in these 2 weeks, any doubts, we can discuss on the 30th. I will ask the NPL team to send you the mail of the personal end of the sessions. Okay, we have the last question for this session. Find the power dissipation. Power dissipation will be directly voltage multiplied by current flowing through the circuit. So, we got this circuit only. So then you have the circuit. What you will do is there are two paths, this path and this path. If you have assignment of the same type, what you will do is you will find the IDS current flowing through the circuit and you will just directly use BJT multiplied by IDS. This will be your power dissipation number one. And another will be biasing current here. Let's say this is I bias, which will be, let's say this is has some value, VDD minus VG by R1. So you use this current I bias, and then you can directly write the power dissipation the bias as what are the formula? You have I square R, you have V square by R, right? Use any of the feasible formula for your calculations. All right, use these formulas. This is transistor dissipation, VDT multiply IDS. And how will you find IDS? Get the transistor in saturation. So this will be Kw by L VGS minus VTH whole square. Okay, just do this. If you're not able to do this, please let me know. So this is this for this week. If you don't understand any of the questions, you can just directly uh, mail me or comment on comment on the YouTube or NPTEL forum section as well. So any further questions before we end this session? I will upload the video and also share the slides. Are you able to access the slides? Do you have access to the slides and the videos, YouTube videos? Okay, so I guess we can end the session and see you next time. Thank you for joining.